In this video, we're going to take a look at how to represent a triple bond forming with Lewis structures, energy level diagrams, and orbital representation. So the example we're going to follow is our molecule here, C2H2. And what we want to do is we want to start off by drawing its Lewis structure. So if you go through the Lewis structure drawing process, you'll get a triple bond between the carbons, and then you'll get single bond for the hydrogen there. What I want you to notice is that if you look at each of the carbons as central atom, let's call this C1 and C2. If you treat each carbon as their own central atom, they're basically a linear structure because they have two things attached to them. So it's a nice linear and straight structure there. So 180 degree bond angles all the way around. What we're going to do is we're going to go and count the number of sigma bonds. So let's label them. We have a sigma over here, a sigma over here. And don't forget that within the triple bond, you have one sigma as well. Let's just make it the sigma in the middle there. So we have 3 sigma bonds. Some of those are CH sigma, and then one of those is a CC sigma. So we have 2 CH sigmas and then 1 CC sigma. In terms of pi bonds, since it's a triple bond, we have a pi bond here and a pi bond there. So we have 2 pi bonds, and don't forget that the pi bonds are made from unhybridized orbitals, right? So these are made from unhybridized orbitals. So that's just a little reminder that these are made from unhybridized orbitals. And then we can go and figure out the hybridization of the different atoms. So we'll go and we'll figure out the hybridization of C1 over here, and there's only 2 regions, S and P. So this is sp hybridized. The hydrogen is just S, and C2 is sp hybridized as well because there's only 2 regions, S and P. So the CC sigma bond is an sp sigma direct overlap, and the CH is an SP S sigma direct overlap. So we kind of know what we need to draw at this point. We know what type of hybridization we need. And what you'll notice is, the carbon is sp. And remember that p has 3 orbitals. So this is made of 1s, 1p. So 2 orbitals of the p sublevel are left behind because there's usually 3 orbitals there. We only used 1. So we're going to have 2 unhybridized for each carbon. And that makes sense because we have a triple bond in this case rather than a double bond. So you can start looking at that, and that'll help you to make your diagrams overall. So let's start by making our energy level diagrams for the simplest ones. We'll make it for our H's first. So energy level diagram for H over here. We have 1 electron, that's 1s. And then an energy level diagram for another H over here. 1s, 1 electron. And we'll put our E there. And this again is, the reason I knew that is because it's 1s1, 1s1. So we'll draw an energy level diagram for, let's say, carbon number 1 over here. We'll call this carbon 1. And so we'll have, what I'm going to do is I'm going to skip, I know it looks like chlorine now. Let me rewrite that as carbon 1. I'm just going to focus on the valence electrons for this one, just to make our lives a bit easier. Those are the ones involved in the bonding. So this is carbon 1. I'm not going to draw the 1s in there. I mean, I could have, but I can skip them, especially when you have more electrons, eventually you just want to focus on valence. So we have our 2s, and then we have our 2p. And we know that we want to form 2 bonds, 2 sigma bonds, I should say. So 2 direct overlaps. So we need at least 2 unpaired electron, 2 single ones. And we do have that. But the problem is that we also need some unhybridized electrons to do some indirect overlapping. And we don't have that yet. So we need to create that. And we want to get an sp type hybridization. So we're going to do a promotion. We're going to do an electron promotion over here. And we're going to mix. And when we mix, we're going to end up with only really the S and the P here mixing. So there'll be an intermediate level. So this is SP, SP. And they're available for some sigma bonding for a CH and a CC bond. And then the other two will stay at their original energy level. So this one and then the one that was promoted will stay there, unhybridized. Like that. So we have that created. And now we'll do our C2. It's essentially the same as C1 because it's also sp hybridized. I'm just going to draw the valence electrons, a 2s, and then the 2p. Now remember, we need to form 2 sigma bonds. We need 2 unpaired electrons that are available for bonding, which we have, but we also need to form a pi bond. So we need some unhybridized electrons. And we don't have unhybridized single electrons right now, so we got to create that through the electron promotion process. Let's call it EP. And then we can mix. And when we mix, we've seen that we have sp hybridized carbon, which means we only want to mix one s and one p. There and there at some level in between them, like this. So we have 2 sp orbitals now. And they are 2 sp because they're at energy level 2. And the other unhybridized ones remain at their original energy level right there. Unhybridized. So now what we're going to do is we're going to go and circle where all the different parts are from. So let's start with our CH sigma from carbon number 1 and H. So that would come from this overlap here and this overlap here. So that's a CH sigma. We'll do the CH sigma from carbon number 2 and H. So this one. That would be SP and S. So we've just explained that. And we could say that the CH sigma bonds are direct overlaps between 1s of H and 2sp of carbon. Let's go and explain the CC sigma bond. So this one over here, that's between the sp of carbon 1 and the other sp of carbon 2. So our CC sigma bond is the direct overlap between the 2 sp of each carbon. And now we need to explain our pi bonds. We have 2 pi bonds. So let's do one color for each. We'll do orange for the top one here. That's just an indirect overlap between one hybridized p of one carbon and the other hybridized p of the other carbon. So actually what I want to do is I'll do that as a broken lined circle. Or dotted line circle. Whatever sounds better there. And then the other pi bond, let's do a little pink color there, is indirect overlap between unhybridized p of one carbon and the other unhybridized p of the other carbon, like that. So those are indirect overlaps. Drawing that out there as indirect overlaps. And then same thing here. Indirect overlaps. You don't really have to do all this that I'm doing here and just showing you their indirect overlaps there. So we can explain the pi bonds as being, so the C pi bonds are sideways or indirect overlap between the unhybridized 2p orbitals of each carbon. And so now our final step, we've done this with a Lewis structure, energy level diagram representations, and words. Our final step is really just to draw this out to show what it looks like as an orbital representation. So as usual, what I like to do is I like to start off by drawing just the carbons and focusing on the sigma bonds. So we'll do the first sigma between the carbons over here. We have an up, down, and then we'll do the, so that's our sigma over here. It's our SP sigma. And then we'll do a sigma between the carbon and the hydrogen. Up, down arrow. So this is an SP and an S from the hydrogen. And then it's going to overlap a bit there with my writing there. It's okay. Up, down arrow here. This is an S and SP from hydrogen carbon. And now we have to do, it gets a little bit messy here, but we have to do our overlapping, our indirect overlap with our unhybridized orbitals. So we'll do the orange one first. So that's going to be one of the unhybridized p electron in there, and then single electron in there. And this is going to be the first pi bond. And then we'll do our other one. I'm going to do the other orientation for the P. So we'll do it sort of this way. Like that. And there's going to be some indirect overlap with the pink there. And a bit messy there. Sorry for the crossover. The pink there. And so this is going to be our other pi bond forming there. And so what we've done is we've shown our two pi bonds, we've shown our sigma bonds, and so between our carbons we showed our sigma bond and our two pi bonds, and between our carbon hydrogen we showed our sigma bonds. And so we've represented this type of bonding in multiple ways with the Lewis structures, with the energy level diagrams, and with the orbital level diagrams, as well as we described it using some words. And to finish off, we'll do a nice easy example here where we have to count the total number of sigma bonds and pi bonds. So let's go count the number of sigma bonds. You can pause the video and try it yourself first and then see if you're on the right track. So for the total number of sigma bonds, I would have 1, 2, 3, 4, 5, 6, 7. Don't forget there's a sigma bond in here. That's 8 sigma bonds. And then for pi bonds, there's a triple bond. So that means there's 2 pi bonds there. 2 pi bonds. And then, did I miss something? Let me just double check if I missed something. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Whoopsies. That should be 9 sigma bonds. I miscounted. So 9 sigma, 2 pi. Very easy to miscount if you're not paying attention. Let's do the sigma bonds in this one here. So I'm going to start with essentially every bond you see, it has a sigma in it. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. 12 sigma. And then for the pi, let's go look at our multiple bonds. This is a double bond, so 1 pi, 2 pi, 3 pi. So here we have 3 pi bonds. And now we're pros at identifying pi bonds, at showing the hybridization of molecules, the shorthand way of showing it with the orbital energy level diagrams, and of also showing it with the orbital representations and words. And one last thing to finish off before we go and end this video is this is an interesting molecule you'll learn about in organic chemistry. You'll notice there's a lot of resonance opportunity. You can draw the double bonds in different places. So for example, I could have drawn it. I'm not going to show all the carbons, just going to draw kind of the main skeleton here. You can draw the double bonds here, for example, instead, and other areas. Because you can draw the double bonds in so many different ways, rather than representing this structure here, this common organic structure, with its resonance every single time, what we actually do is we represent it like this. We show the entire structure drawn like this with a circle there to show that the structure has a lot of resonance, essentially, and that it's going to be formed of some hybrid of that resonance that you can display. And this is a common molecule used in organic chemistry. It's called benzene. So it's good to become familiar with these molecules and the way they're set up now, because organic chemistry is going to be all about these carbon-based, hydrogen-based molecules going forward.